Hello everybody, this is FE Peer Review. The date is the 19th of December 2022. My favorite map projections number 4. Equal Earth projection and natural Earth projection. We're going to look at two in this video. As you may recall, in the previous video we looked at the mole-wide projection, which was a pseudo-cylindrical and non-conforming projection. I introduced both those ideas and we discussed them a little bit. This here's the mole-wide that we looked at. Along the way, I mentioned briefly the concept of the equal area projection, which the mole-wide is an equal area projection, and how area and shape accuracy cannot both be maintained in a projection. You have to pick one or the other, or you can be inaccurate in both. This is the equal area projection that we looked at briefly in that previous video, and it's the one we're going to look at more today, along with the natural Earth projection. But before we get on to that, I want to touch briefly on another subject I mentioned in passing in that same previous video about the Boston Public School choice of wall maps for their classrooms. You may recall I mentioned in 2017, Boston Public Schools announced they were going to transition to a new map in their classrooms. They were going to use what's called the Gall-Peters projection, which we see a copy of here in this article from The Guardian. Now, I do enjoy Guardian reporting. It was reported in a lot of different journals, and this was just the one that came up quickly when I did a Google search. So I'm not critiquing The Guardian too much here. I was kind of amused by their headline, Boston Public Schools map switch aims to amend 500 years of distortion. Distortion being the word which amused me here, because as we saw in that previous video, the Gall-Peters map, although equal area, is extremely distorted. So I thought it'd be interesting to take a brief look at the choice the Boston Public Schools made to go from what I'm assuming was probably a Mercator projection. I couldn't figure out what they were using before 2017, but chances are Mercator, to a Gall-Peters. So we're going to take a brief look at the kinds of distortions involved in those maps. And then we're going to look at the equal area and the natural area maps to see how those distortions are handled. I am going to conclude at the end of this that Boston Public Schools was probably misguided in their choice of a solution to the problem they were identifying. Now, they identified a particular problem, which we'll get to, but I'm not so sure they went the right route as far as the solution. And that probably had to do, to some extent, with their problem statement. Looking for a good example of a Mercator projection today, a map that you might have found in a school classroom, I came across this and just found it delightful. It is pre-World War I. I'm guessing sometime between 1900 and 1915. 1917, somewhere in those first years of the decade. It's still Russia. It's not yet the USSR. Greenland up here is called Danish America. There's lots of fun little oddities, but the thing that I really enjoyed the most was these very vibrant red lines going everywhere. These are telegraph lines. And, you know, in the 1910s, telegraph united the whole world in its ability to create instant communication. It was the real breakthrough. We make a big fuss about the internet, but really it was the telegraph 120 years ago or more, I don't remember exactly when it was introduced, that created the first worldwide instant communication network. And it really had a huge impact on the development of society. So this is probably similar to the maps you would have found in schools before the First World War, and probably all the way up to the Second World War, even into the 50s. They would have had an updated version, but pretty much the same thing. Of course, I'm doing this video from an American perspective. I'm talking about the Boston Public School. So it's no surprise that the map that I found has America front and center, right in the middle of everything. It's worth noting that most of the telegraph lines actually do. It really was in the middle of everything. Then most of the telegraph lines, most of the world's communication networks were connecting the northeast of the United States to the west coast of Europe. So yeah, you know, representationally, conceptually, here I am gesticulating and you can't see my hands. Conceptually, this network of communications here really was the center of the world in terms of what was changing in the world and what was moving the world's economies. So this is a Mercator map, and it gives you extreme distortions in the polar regions where pretty much nobody lives. So the question is, how much is it actually distorting the zones across the middle? We're going to take a look at that and compare the amount of distortion we see in the populated parts of the map with the amounts of distortion we see in the Galpeters. Okay, I'm inserting a little edit here. Before we move on to looking at all those nice proportions of continents and things, I wanted to go off on a little bit of a tangent. This video is going to be a little bit longer than the earlier ones, but I think you'll find all this amusing. I hope so. So there's the Mercator map with the United States at the middle. I got it in my mind. What about other countries? What about the maps that they used or may have had in their school classrooms? And I thought, let's check out China. So I found a couple of articles that were interesting. For a start, it appears that the Chinese basically believed the Earth to be flat up until the 1600s. The general idea was that it was a square covered by a dome of some kind, and the name of the country of China in Chinese is Zhongguo, which means the middle country, and they placed their country in the middle of the square. So a couple of fun articles, I'll put links in the description. Anyway, this one here, what does China's version of the world map look like? This is somebody who's been to China and knows Chinese public schools, and this is the map that they use in the Chinese public schools. Now, I don't know what projection this is. There are a lot of projections that have a similar outline. I don't think it's an equal area projection. It's probably a compromise between the two. It's non-conformal. It's not cylindrical, which we can see because the latitude lines aren't parallel. But interestingly, it divides the continents with China fairly near the middle of the map, and very logically a break through the middle of the Atlantic, whereas typically we often see the break on other maps being through the middle of the Pacific. So by breaking it through the middle of the Atlantic, it places China closer to the center of the map and still manages to keep the continents pretty much unbroken. So as it turns out, though, there were some astronomers apparently in the 1100s who were coming to the conclusion that the lights in the sky, in particular the planets and the moon and the sun, were some kind of spherical objects. It's not clear whether those same scientists from the 1100s were including Earth as a spherical object in their statements, in their writings. That's not clear. But they had begun to come across the idea of at least the sun and the moon being spheres. Now, it seems that they finally didn't come around to the idea of a spherical Earth until the Jesuits arrived. Jesuit missionaries in the early 1600s arrived in China and introduced the idea to the Chinese court, and the rulers and the intellectuals of the Chinese court came to the conclusion that the Jesuits were correct. So the earliest maps, there are early maps from that time made by the Jesuits for the Chinese court, which depict a more accurate map of the Earth, still placing China near the center, but incorporating spheroidal geometry. So that's a little bit about Chinese school maps. Let's take a look at that school map up close. Where'd it go? So there it is. That's the map that you see in a lot of schools in China. Now back to our main topic. So I had a bit of fun with this. What I did was I went to Google Earth and I positioned the upper 48 states, the continental United States minus Alaska, in the center of the image here, so that we're pretty good as far as shape accuracy. And I measured the distances east, west, and north, south. And then I did the same for the continent of Africa. I measured the distances east, west, and north, south from the farthest points. And I took those proportions and created two rectangles. Here we see the Mercator Map, and I've overlaid the two rectangles with the proportions based off of Google Earth. So we have a red horizontal rectangle surrounding the United States that's proportional to what's on Google Earth. This is not a highly accurate thing here. I'm just trying to get something that's pretty close, give you a good idea of the shapes. So we've got the red rectangle surrounding North America, the United States, 48 states. And then we've got the other rectangle that I created surrounding Africa. And so if we look at these two rectangles, I will zoom in on the Africa one. I have the proportion of the rectangle is a match for what I got off of Google Earth. And then I've made the width of the rectangle align with the east and west coasts of African continent. I put the top and the bottom splitting the difference. So we see that there's a little bit of landmass poking at the bottom and a little bit of landmass poking out at the top. So this Mercator Map shape is slightly stretching the continent of Africa in a north-south direction compared to the east-west. We can see to some extent we can get a rough idea of the amount of distortion involved here. And I'm going to characterize this as minor compared to what we're going to see soon. Here we're looking at North America, and I've done something similar. I've made it fit north-south, and I've aligned the eastern edge, and we see that it distorts the continent slightly. I'm a little bit over, but the distortion is really minimal. Very small amount of distortion of shape for the lower 48 states themselves. Now I've done one more thing. I copied the profile of the United States from this map and pasted it over the northern part of Africa here to get a sense of area relationships between these two and try to identify to what extent this map is distorting the areas relative to each other. I'll zoom in a little bit. I aligned the west coast of the American map with the west coast of Africa, and as you can see, it extends across with the tip of Maine here just touching the Arabian Peninsula. So that gives you a sense of comparative sizes according to this map, comparative areas as well. So we're going to take a look at that in another application here. Some of you may already be familiar with thetruesize.com. It's a great website. It allows you to compare land masses. I've got the United States here, the 48 states, and as you can see, if you put it in different parts of the map here, it gives you the relative sizes. So I'm going to put it over the northern half of Africa and get pretty much the same alignment as I had on that Mercator map. And what we see, if we align the western edges, is that Maine doesn't quite reach to the Saudi Arabian Peninsula. It reaches as far as Egypt. And if we look at it in the north-south direction, it's going from Texas being there down at the Gulf of Guinea. It reaches about halfway through Algeria. So this shows us, in comparing this to the previous image, we can see that this Mercator map is stretching the United States east-west and extending it a little further than it actually is. In terms of north-south, it's not a big difference. In terms of north-south, it's a pretty near match to the TrueSize.com imagery we just looked at. It comes up to about halfway through Algeria. If I were to take this analysis one step further, I think what I'd do is I would make a copy of this red blob here and shrink it down just a little bit. It really ought to come to about here. But I think that gives you a feel for the extent of distortion in this Mercator map when we're looking at regions from about 45 south to 45 north. Beyond about 45 north, you start to get a lot more distortion. But the vast majority of the world's population is to be found in that zone. So in the populated areas of the world, this map isn't all that distorted. Certainly compared to the Gall-Peters, which we're going to see next. So here's the Gall-Peters map. This is the map that was adopted by the Boston Public Schools. And it is an equal area map. So the areas of the United States and Africa are, in fact, correct comparatively relative to each other. However, it exhibits extreme shape distortion, as we will see here. I have taken my two little red bounding boxes, which represent the actual proportions of the United States and the continent of Africa, and I've overlaid them on this map. Now, it gets the United States pretty good. You've got Florida sticking out pretty far down here. So it's stretching the United States in the north-south direction. Quite a bit. More than the Mercator map was. It is a much less representative of the shape of the United States. Taking a look at Africa, we see just how extreme the distortion is in terms of shape. The African continent is actually only a few percent longer distance north-south than to east-west. It divided north-south into 100 parts, and east-west was 94 parts. So you can see that the map here exhibits really extreme distortion. So my question to the Boston Public Schools officials is making equal area the absolute criterion, you have effectively eliminated shape as a criterion, shape accuracy. If the point of this changeover was to provide students with a more correct perception of the Earth, have we really accomplished that by focusing only on area at the complete and absolute expense of shape? Wouldn't shape also be an important factor in understanding the shape of the Earth? Now, the simple solution, of course, is to put a globe in every classroom. But we're going to figure that the simple solution is rarely the one that gets picked because it's simple. We need to complicate things. So what was the reason behind this? I'm not going to try to get into the heads of the Boston Public Schools officials, but I think the result of their decision was to provide students with a map that provides a much more distorted view of the Earth than the map that it replaced. Returning to the Guardian article from 2017, at the time, Boston Public Schools map switch aims to amend 500 years of distortion. Don't you just love that word? Okay, so that's my ramble about Boston Public Schools and shape and area. Now let's take a look at some good maps. My bad, I almost forgot to show you this particular slide. This is the same Gall-Peters map with what's called TISO overlaid, which is the little red circles we looked at in the previous video that show you the distortion. So here we see the TISO diagram. Let me fiddle with the opacity a little bit. So those little orange circles, orange ellipses, are supposed to be circles, and the extent to which they're not circles gives you a sense of the distortion you're seeing on the map. So these little ellipses all are of the same size because this is an equal area map, so no distortion on that front. But as you can see, they are extremely distorted in terms of shape, with the largest distortion happening across the line of the equator. Vertical distortion along the line of the equator, horizontal distortion near the poles. So there you go. That's hard facts about distortion in the Gall-Peters map. So here is the projection called the equal Earth projection, and it's a pseudo-cylindrical projection, and it is an equal area projection, like the Gall-Peters map. However, it has much less shape distortion than the Gall-Peters map, and that's what we're going to look at. This is where we introduce Tom Patterson. I mentioned Tom Patterson in the previous video. He was the instigator of the creation of this map in direct response to the Boston Public Schools' decision to adopt the Gall-Peters map. He was a retired National Park Service employee with an interest in mapping. He went to Esri, great company that does mapping, and got a couple of their engineers, Bernard Jenny and Bohan Savrich, to work with him to create what he thought would be a better equal area map, which is what we're looking at now, the equal Earth map. The Wikipedia has a nice page on it. It's got all the math involved down here. For those flat earthers out there that are trying to make their own flat Earth map, you might want to look at this. And let's see, what more can I tell you about it? Let's take a look at some of the distortions involved. So we have the Greenwich meridian running up and down through the center. We've got the equator running across the middle. we see that it's a non-conformal map in that the longitude and latitude lines do not cross at right angles except at the Greenwich meridian in the equator and at each end of the equator. It conveniently puts Greenwich meridian in the middle and allows you to maintain almost complete continents. The tiny little bit of Russia that got cut off in the northeastern part of Russia. The shape distortion becomes more extreme the further north or south you go, the closer you get to the polar regions. Now let's turn on the Tissot diagram here. I'll bring it in with opacity. Again, it's our little orange circles. The extent to which they diverge from being circles and move towards ellipses gives you a sense of the amount of distortion in that part of the map. There's the Tissot diagram. All in all, a pretty good representation. It's stretching things north-south fairly considerably. Let me increase the opacity some more here. We see from these circles along the equator that they're rather stretched out vertically. At the mid-latitudes, we've got less distortion, especially in the middle of the map, more distortion towards the edges. So it's a good compromise if maintaining equal areas is an absolute criterion and cannot be wavered from, which I think the Boston Public Schools officials were wrong about. It's definitely a vast improvement in terms of shape accuracy over the Gall-Peters map. But now let's look at one more that I find quite interesting. It's called the Natural Earth Map, and it was created by Tom Patterson some 5 years before in 2012. It's neither equal area nor shape accurate. It's a compromise. This is the Natural Earth Map, and we don't need to spend a whole lot of time on it. There is a Wikipedia page, which I'll show you here. This here is the Wikipedia page for the Natural Earth projection. And again, you've got all the math you could ever want right down here. Tells you how it was made. It's a pseudo-cylindrical map, neither conformal nor equal area, but a compromise between the two. Let's take a look at the Tissot overlay to get a sense of the amount of distortions going on here. So what do we see? Well, across the equator, across the line of the equator, they're pretty nearly circles, so shape accuracy is pretty good along the equator. The next row of circles is 30 north and 30 south latitudes, and if we look at the main part of the map, not the very edges, we see that again the shape accuracy is pretty good. They're pretty nearly circular. We see that these circles are slightly larger than the circles along the equator, which means that relative to the equator, this is inflating the areas a bit, but not as much as other maps. And then as we move closer to the poles, we get more area inflation. So yeah, we're getting Greenland a little bit too big compared to Africa again. Of course, Antarctica is oversized. As you get to the extreme polar regions, you get the most distortion. But all in all, you see that the bulk of the area where people actually live has fairly minor shape distortion and fairly minor area distortion. It is, in my opinion, an excellent compromise. Another word that might be useful is balance, an excellent balance between two different factors in understanding the shape of the Earth, which is areas and shapes. Shape accuracy and area accuracy. This map has achieved balance. So my little message to the Boston Public Schools officials was perhaps balance might have been a consideration rather than just size. It's true, size matters. But so do other things, such as shape. That's my rant for the day. I hope you found these maps interesting. In the next video, we'll probably be taking a look at a Mercator map, or maybe a couple of them, and looking at them in terms of how they were used for navigation before we had all our wonderful modern technology. I feel like I've covered the social/political aspect more than enough here, and I don't want this to become a political rant. So we'll move on to more technical ship navigation using a Mercator map, how it was done. And that'll be in the next video. So I hope you like this. If you did, remember to click the like button. And of course, if you haven't subscribed, please do. there'll be a few more of these map videos, and maybe eventually, if I can get myself to do it, I'll get back to bashing flat earthers again. Kind of got annoyed with them for a little while, but we'll come back to them too, eventually. In the meanwhile, we're having fun looking at flat earth maps, all kinds of flat earth maps. Okay, have a great day. Talk to you all soon. Bye-bye.